Hi everyone, I welcome you all to this video. In this video, we'll see some questions from week 4 of PDSA. So let's begin with the first question without wasting our time. It says for an undirected graph consisting of 6 vertices and exactly 3 connected components, what is the maximum possible number of edges it can contain? So we have an undirected graph which has 6 vertices and exactly 3 connected components. Those who are not familiar with connected component, you won't be able to solve this question, and all the questions which will have connected component. So I'm assuming a lot of you are not familiar with it. Therefore, I'll begin with explaining what a connected component is. So, uh, yeah. So, what is a connected component? So, before delving deeper into its definition, I would like to present you with some examples, and we'll try to understand this from that example. We'll try to figure its definition out with the help of that example. So, I'm gonna draw a graph here. A, B, C, D, E, and F. So this is a graph. Now, have your eyes on this one component. If I ask you, are A and B connected? What will be your answer? Think a moment and tell me. Obviously, it is apparently visible that these two vertices A and B are connected through this edge. So we'll say, yeah, these two vertices are connected. If I ask you, are A and C connected? You'll say it is not directly connected, but yeah, if I'm at vertex A and if I want to reach, let's say you are here and you want to reach to vertex C, you can do that via reaching B first, then you can reach vertex C as well, right? Similarly, let's say you are here at this vertex, okay, and I ask you, can you travel to vertex A? You'll say, yeah, I can do that. Can you travel to vertex C? You'll say, yeah, I can also do that, right? Through this graph, this edge and this edge. So if you notice in this particular component, you can travel to each vertex from a particular vertex, right? If you start from A, you can cover both these two vertices, B and C, right? So in other words, I can say each vertex is reachable from every other vertex. And this is the condition for a component to be a connected one. I'm repeating it again. If you can reach, if you can explore all the vertices present in a component from a particular vertex, that component is that component can be considered, or that component is indeed a connected one. Okay, so every vortex is reachable from every other vortex. It simply means that particular component is connected. Now, let's see this. Uh, if you are if you are at D, you can reach E. If you are at E, you can travel back to D. Therefore, this component is also connected. What about this one? This alone vortex. Can we say something about connectivity, like whether it is a connected component or not? Take a moment and think about it. It is a connected component. Why? Because you can reach to vertex F itself. Obviously, you can not reach to other vertex because there is no edge which connects uh, F with other vertex. So you can only reach to vertex F itself. Therefore, F is also a connected component. So in this graph, we have three connected components. Let me give you one very interesting example. It will help you understand more things about a connected graph. Then we'll come to its definition. Uh, let's see. A, not A this time. Maybe. Let's say M N O P. If I ask you, can I consider this particular component as a connected one? Can I say M N N O is a connected component? What do you say? We'll check. We'll check if every vortex is reachable from every other vortex or not. Let's say let's say you are at here. You are at M. So you can reach to N via this edge. From N, you can reach to O via this edge. Similarly, if you are at M, you can reach M. You can also reach O. If you are here, you can travel back to M as well, right? So uh, it satisfies the condition of a connected component. Every vortex is reachable from every other vortex. However, you can also reach to this vortex. If you are at M, you can travel through N and you can reach this vortex as well. If you are at O, you can travel through N and you can also reach this vortex. If you are at P, let's say you are here and you want to reach vortex M, you can do that as well. You can take this route and you can reach. If you want to reach O, you can do that. Therefore, we cannot exclude P here. We had to include P. P is one more vortex which will come under this set. All right. So, and then it will form a connected component. So this entire component is connected because you can reach every vortex from a particular vortex. Okay, so we cannot miss out P from this connected component. Now I'll define what a connected component is and you will be able to understand the definition better now. I need a blank page. Yeah, let me write it here. So it is a maximal set of vortices where each vertex, I'm not sure, yeah, should be R. Each vertex is reachable. Mind my spelling mistakes. Uh, where each vertex is reachable from my spelling as well as my writing. I know my writing is not very good, though it is good on paper, but I'm not sure why I'm unable to write with that beautiful handwriting over here. Uh, is reachable from every other vertex. Notice this word maximal set. It means we need to include all the vertices that could come to form a connected component. In the previous example, we were missing out on P. P had to be part of this set, okay? Because we could also explore P from any vertex of this component. Therefore, P was supposed to be part of the set. That's why it is written the maximal set of vertices. We need to include all the vertices which will form a connected component. Okay. Now, I'd like to summarize it. So, if someone asks you what a connected component is, you can simply say, if you find a, you can say this definition as well. It is a maximal set of vertices where each vertex is reachable from every other vertex. Remember this maximal set of vertices from where each vertex is reachable from every other vertex. All right. Now, as we understood what a connected component is, now we are in position to solve that question. Now let's get back to that question. Okay, so for an undirected graph consisting of 6 vertices and exactly 3 connected components, what is the maximum possible number of edges it can contain? So we have an undirected graph which has 6 vertices and exactly 3 connected components. So let's write it first. Uh, undirected graph, vertices, we have 6 components, connected components. I'm writing here connected components. We have 3, and what we need to find, what is the maximum possible number of edges it can contain. We have to find the maximum possible number of edges. Maximum possible number of edges. Now, 6 vertices, 3 connected components, and we have to find maximum possible number of edges. All right. So when do we have when what are the chance when do we get maximum edges? When is that happen? If you have, let's say, two vertex only, two vertices only. Okay, I'll draw it here. Let's say you have one. What is the maximum number of edges that you can have between these two vertices? One, right? One only. Let's say we have three vertices. Let me draw one more. We have three vertices. Now, how many? Uh, what is the maximum number of edges that we can have? We can draw here. From here, we can have three. Okay. Let me insert one more blank page. Yeah. Uh, let's say I draw one more vertex. Now I can draw one more edge over here, over here. Uh, now one here. Yeah. So now how many edges we have now? We have one, two, three, sorry, three, four, five, sorry. So, okay, let me use the cursor. One, two, three, four, five, six. So we have six. So, are you able to notice a pattern? As the number of vertices are, as the number of vertices increase, edges are also increasing, right? So since we have six vertices, we need to distribute this six vertices such that we can get three components. So let me do the distribution. Uh, it starts lagging again. I don't know what is happening. Let me reinsert. All right. Let's proceed. So I'm distributing six vertices such that we could have three connected components. Two, two, two. Okay. Now three, one, two, four, one, one. So in this, we could have maximum number of edges. That would be three, because three is the maximum number of vertices. In this example, this particular example, yeah, we could have six vertices. It's the same that I show you previous. Uh, yeah, see Here also we had four vortices, and which made and therefore we had total six edges. So the maximum number of edges that is possible in this question would be six. I hope you understood. Thank you for watching this video. See you in the next video. Till then, bye bye. Take care. Happy learning.